Welcome. In this video, we will explore data structures and algorithms, often abbreviated as DSA, specifically focusing on key concepts and frequently asked topics in coding interviews. Understanding DSA is crucial for any aspiring software engineer. Let's dive in and see why DSA matters. First, DSA provides the foundation for problem solving. It equips you with the tools and techniques to approach coding challenges effectively. Second, it is a standard assessment in technical interviews. Companies use DSA to evaluate your coding skills and problem-solving abilities. Third, mastering DSA improves code efficiency, making your programs run faster and use resources more effectively. Finally, learning DSA develops analytical thinking, enabling you to break down complex problems into smaller, manageable parts. We will be covering topics such as arrays, linked lists, and trees and graphs. Let's delve into the array data structure. Arrays are fundamental in computer science and are widely used. First key characteristic of arrays is contiguous memory allocation, meaning elements are stored next to each other in memory. Second, arrays provide constant time access, denoted as big O of 1, which allows for quick retrieval of elements using their index. In many languages, arrays have a fixed size, which means you need to specify the number of elements it can hold in advance. The indexing in array always starts at 0. Let's discuss time complexity for various array operations. Accessing any element in the array takes big O of 1 time. Searching for an element in an unsorted array takes big O of n time, where n is the number of elements. Inserting or deleting an element in the middle of an array takes big O of n time because you may need to shift other elements. Now, let us look at a common array operation using a Python code snippet. This code defines a function findMax that finds the maximum value in an array. It initializes max value with the first element and then iterates through the array, updating the max value if a larger element is found. Finally, let's discuss some frequently asked array problems. These include the two-sum problem, where you find two numbers in an array that add up to a specific target. Another one is the maximum subarray problem, where you find the contiguous subarray with the largest sum. We also have array rotation and find duplicates problems. Strings are another essential data type in programming. Let's explore some common string manipulation techniques. These techniques include substring extraction, which is retrieving a portion of a string. We have pattern matching, which is finding occurrences of a specific pattern within a string. String reversal is reversing the order of characters in a string. Also, there is palindrome checking, which is determining whether a string reads the same forwards and backward. Next, we have character frequency analysis, which is counting the occurrences of each character in a string. Lastly, there is lexicographical comparison, which is comparing strings based on dictionary order. Let's examine an example of a palindrome check using a Python code snippet. This code defines a function as palindrome that checks if a string is a palindrome. It removes non-alphanumeric characters, converts the string to lowercase, and then compares the string with its reverse. Hash tables are very powerful data structures used for efficient data storage and retrieval. Let's start with the key characteristics of hash tables. Hash tables store data in key value pairs. They offer big O of 1 average access time, making them extremely fast for retrieving data. Hash tables use hash functions to compute the index for each key. Collision handling is a crucial aspect where multiple keys might map to the same index. Here we have a diagram which shows how hash functions work. The diagram shows a hash function taking a key as input and mapping it to an index within the hash table, which is in the form of buckets. Here is an example of hash table implementation. The Python code defines a function called char frequency that counts the frequency of each character in a string using a hash table. Finally, let's discuss some common interview problems involving hash tables. There is the two-sum problem, where you need to find two numbers in an array that add up to a specific target value. Valid anagram is where you determine if two strings are anagrams of each other. Another problem is group anagrams, where you group words that are anagrams together. Now let's explore linked lists, a fundamental data structure in computer science. First, linked lists use non-contiguous memory allocation, meaning elements are not stored next to each other in memory. Unlike arrays, linked lists have dynamic size, which allows them to grow or shrink as needed. Inserting and deleting elements at a known position in a linked list takes big O of 1 time, which is very efficient. Searching for an element in a linked list takes big O of n time, where n is the number of elements. There are different types of linked lists, including singly, doubly, and circular linked lists. Some of the common operations performed on linked lists are inserting at the head or tail, deleting at the head or tail, searching for a value, and reversing a linked list. Here is a diagram illustrating the structure of a linked list. The diagram shows a linked list with a head pointer and several nodes, each containing data and a pointer to the next node. The last node points to null. Here is a Python code snippet which defines the node class. This class is used to create individual nodes in a linked list, where each node contains data and a pointer to the next node. Let's discuss stacks and queues. First, let us understand what a stack is. Stacks follow the LIFO principle, which means last in, first out. It has 3 main operations: push, which takes big O of 1, pop, which also takes big O of 1, and peek, which also takes big O of 1. Stacks have numerous applications, including function calls, undo operations, and expression evaluation. A visual representation of a stack shows elements being added and removed from the top, following the LIFO principle. Now let's learn about queues. Queues follow the FIFO principle, which means first in, first out. It has 2 main operations: enqueue, which takes big O of 1, and dequeue, which also takes big O of 1, and front, which also takes big O of 1. Queues are used in applications such as BFS, print queues, and message queues. The visual representation shows elements being added to the rear and removed from the front, following the FIFO principle. Let's take a look at tree data structures. First, let's explore the terminology used in trees. A tree consists of root, parent, and child nodes. Leaf nodes are the nodes that have no children. The depth of a node is its level from the root, where the root is at level 0. Height is the longest path from a node to a leaf node. Traversing a tree involves visiting each node in a specific order. The commonly used tree traversal methods include pre-order, which visits the root first, then the left subtree, and then the right subtree. In-order traversal visits the left subtree first, then the root, and then the right subtree. Post-order traversal visits the left subtree first, then the right subtree, and then the root. Lastly, there is level order traversal, which uses a BFS approach to visit nodes level by level. Here is a visual representation of a binary tree structure. The diagram illustrates a binary tree with various nodes, showcasing the hierarchical relationships between them. Binary search trees, or BSTs, are a specific type of tree data structure that provides efficient ways to store and retrieve data. Let's explore the properties of a BST. In a binary search tree, all nodes in the left subtree are less than the root node. All nodes in the right subtree are greater than the root node. Each subtree is also a BST, meaning that these properties hold recursively for every node in the tree. In-order traversal of a BST gives a sorted result, which is a useful property for many applications. Here are some common operations performed on BSTs. Searching involves comparing the target value with the current node and moving left or right depending on whether the target is smaller or larger. Inserting a new node involves finding the correct position to maintain the BST properties and adding the node there. Deleting a node involves handling different cases based on whether the node is a leaf, has 1 child, or has 2 children. Finding the minimum or maximum value involves finding the leftmost or rightmost node in the tree respectively. A visual representation of a BST shows a tree structure with nodes organized according to the BST properties. Here is the time complexity of different BST operations. The average time complexity for search, insert, and delete operations is big O of log n. However, the worst-case time complexity for these operations is big O of n. The space complexity for a BST is big O of n. Let's delve into graph representations and traversals. First, let us understand the terminology used with graphs. A graph consists of vertices, also known as nodes, and edges, which connect the vertices. Edges can be directed, meaning they have a specific direction, or undirected, meaning they can be traversed in both directions. Adjacent vertices, also known as neighbors, are vertices connected by an edge. A path is a sequence of vertices that connect two nodes, and a cycle is a path that starts and ends at the same vertex. A graph can be connected, meaning there is a path between any two vertices, or disconnected, meaning there are vertices that cannot be reached from others. Now let's explore graph traversal algorithms. Breadth first search, or BFS, uses a queue data structure and explores neighbors first. Depth first search, or DFS, uses a stack or recursion and explores as far as possible along each branch before backtracking. Let us look at how graphs are represented. Adjacency matrix represents a graph as a two-dimensional array, where each element indicates whether an edge exists between two vertices. Adjacency list represents a graph using a list of adjacent vertices for each vertex. Here, a visual representation of a graph shows nodes and edges, with annotations for BFS and DFS traversal paths. Dynamic programming, often abbreviated as DP, is a powerful technique used to solve optimization problems by breaking them down into smaller overlapping subproblems. Here are some key characteristics of dynamic programming. Dynamic programming is characterized by overlapping subproblems, where the same subproblems are solved multiple times. It also is characterized by optimal substructure, where the optimal solution to a problem depends on the optimal solutions to its subproblems. Memoization is a top-down approach where the results of expensive function calls are stored and reused when the same inputs occur again. Tabulation is a bottom-up approach where the results of all the subproblems are stored in a table and used to build the solution to the original problem. Here are some common DP problems. We have the Fibonacci sequence, knapsack problem, longest common subsequence, coin change problem, and edit distance. Let's look at the Fibonacci sequence as an example. The code shows two approaches to solving the Fibonacci sequence: a recursive approach and a dynamic programming approach with memoization. The recursive approach has a time complexity of big O of 2 to the power of n, while the dynamic programming approach has a time complexity of big O of n. The space complexity for both approaches is big O of n. Let's move on to sorting algorithms. Sorting algorithms are essential for organizing data in a specific order. We have several different sorting algorithms. Here is a table which compares these algorithms in terms of time and space complexity. It includes bubble sort, selection sort, insertion sort, merge sort, quick sort, and heap sort. The table provides the best case, average case, and worst case time complexities along with the space complexity for each algorithm. Here are some tips for interviews. Quicksort is often the most practical choice, but be aware of its worst case scenario. Merge sort is reliable with a consistent performance, but requires extra space. For nearly sorted data, consider insertion sort. Here is an example of quicksort implementation using Python. When to use which sort? For small datasets, insertion sort is generally preferred due to its simplicity and efficiency. Merge sort is used when guaranteed performance is required, as it has a consistent big O of n log n time complexity. Heap sort is used when memory is constrained as it has a big O of 1 space complexity. Quicksort is often the preferred choice for average performance due to its efficiency in practice. Let us move on to search algorithms and their time complexity. Searching is a fundamental operation in computer science, used to find a specific element in a data structure. The common search algorithms include linear search, binary search, depth first search or DFS, and breadth first search or BFS. Here is a comparison of their time complexity. Linear search has a time complexity of big O of n, where n is the number of elements. Binary search has a time complexity of big O of log n, but requires the data to be sorted. DFS has a time complexity of big O of v plus e, where v is the number of vertices and e is the number of edges in the graph. BFS also has a time complexity of big O of v plus e. Here is an example of binary search implementation in Python. Binary search requires a sorted array, but provides significant performance improvements over linear search for large datasets. Graph search algorithms like BFS and DFS are essential for traversing complex data structures. That is it for this slide. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.